right, so we're starting. Today we're going to start 1.1, which is going to be relations and functions. A relation is a set of ordered pairs. It can be represented with a table, a mapping diagram, a graph, or expressed as an equation. So there are functions, which are relations, but to be a function, you have to be a special type of relation with a special set of requirements, okay, in addition to these. So a function is a relation in which each element of the domain is paired with exactly one element of the range, f of x, where x is the input value. So we want to determine if this set of ordered pairs is a function. So the first thing we always look at are there any repeating x values here? We have a 6 here, we have a 6 here, and a 6, right? So, with that being said, we're then going to look at their corresponding y's. Do they all go to the same y? The only time you can have repeating x's that still remains a function is if they all go to the same y. Since they do not, this is not a function. Okay? Since they go to different y values, it is not a function. Okay? Because it wouldn't pass the vertical line test if you were to graph it. All right? Any questions about that? Okay. Now we're going to talk about the different types of relations that you're going to encounter today and in the future. A discrete relation is a relation whose graph consists of points that are not connected. Okay? So as you can see, we have a set of coordinates here on the coordinate plane. Now these points are not connected, which means I don't know what's happening between those points. I don't know if the function exists between those points or anything like that, or if the relation exists. So this right here is discrete, okay? They are not connected. So that means if you put your finger on this, you can't just get to the next part without having to lift your finger, okay? Now if we look at continuous, a continuous relation is a relation whose domain has an infinite number of elements and it can be graphed with a line or a smooth curve. So in this case right here, if I were to put my finger down at one end and then drag my finger across, I wouldn't have to lift my finger to get to the other side, right? This is continuous, all right? And there are continuous relations and functions, okay? This one happens to be a linear function. And then we have the vertical line test. This is a test that allows us to determine if a relation is a function when it is graphed. So as you can see in the first graphic, do you notice that the vertical line goes through 2 points on the relation? Here and here. Everybody see that? That means that you have failed the vertical line test if you go through more than 1 point on the relation. Now over here, notice that we go through only 1 point on the relation, and if you were to draw a vertical line anywhere on that relation, you would only go through 1 point, which means that this passes the vertical line test. Maybe I'll do it in green. Passes the vertical line test. So does anyone have any questions about determining if you pass or fail the vertical line test? Okay. Now we're going to talk about the difference between domain and range. Domain is all the input values of the function, all of your x's, the left to the right, okay? Makes up the independent variables. They determine the dependent ones. And then a range is the set of values that correspond with the dependent variable, also known as the y coordinates of a function. The dependent variable is determined by x, okay? Like the function machine, it goes in, you get something out. And let's talk about a visual representation of domain and range. Domain is all of the x coordinates. So if you were to take a random coordinate, a point on this relation, it's going to be the x coordinate will be the domain. The y coordinate is the range. Very good, the range. Okay. Now, when we sometimes want to classify domain and range of different functions, we are going to use different symbols. We have an infinity and a negative infinity symbol, positive and negative. This tells us that a function is going on for an extended amount of time in one direction forever. Okay, we can't classify an end, so we say it's infinite. If it's going this negative infinity, this right here corresponds with up and right. And this corresponds with down and left, okay? These ones here, up, down, have to do with the range. And up, right, what do you think they go with? Or right, left, I mean. Domain. Okay. So you don't have to write that, but it's just a little bit of a tip. So let's talk about interval notation. This is a way that we write subsets on the number line to determine or classify what the domain and range is. Okay. So to indicate an endpoint is not included, we use parentheses. Now you also always use parentheses for infinities. Okay, so if you have an infinity on one side, you always use parentheses. Never a square bracket for infinity. You all hear that? Infinity, no square bracket. When you use the square bracket, it looks like this. Okay, you see the difference between the two. One's like smooth and curved, and one's square. When you use a square bracket, you're indicating that point exists on the function, okay? And you use this when we have either a closed circle or we have a solid line that's cutting off there. So let's talk about a visual representation of this. As you can see at these 2 points, you see how those circles are filled in? That means we use the square brackets to indicate that we go from -4 to -2. That means that we're including those values on that interval, okay? The union symbol looks like a U, a capital U, and that means we're also indicating that we're including values between -1 and 1. What's the difference here with the -1 and 1? Are they included? -1 and 1, are they included? No, they are not included. We're talking about all the values between -1 and 1, but not the values themselves. So for example, 0.99 would be included, but when we get to 1, that's where we cut it off. No 1. And then from 1 to 2, 1 is not included, 2 is. And then we have a single lonely value of 4 out here that we just have to throw in. And when you have a single value like this, an isolated value, you just use these curly brackets, which is set notation, to indicate we're also including that 4. So now we're going to use some skills that we just determined to get some of these here. So we're going to start with the ordered pairs. So when you want to list out the domain and range for a set of ordered pairs, the thing I harped on a little yesterday with you guys, see why I have to say it? So, sorry that the lights kind of fell right here. So to determine the domain, sorry, I don't know what's going on with this. To determine the domain, we are going to list out all the possible x values, okay? So that's -1, 0, 4, and 6. And what do you think the range is going to be? The y's. Okay, that's it. So how we determine if this is a function? First thing you do, are there any repeating x values here? No. So if there's no repeating x values, you can automatically say it's a function. Okay? No repeating x's, it must be a function. All right. Next one. We're going to list out the domain, all the possible x's. Now, notice that 5 occurs twice. You do not need to write repeats twice in set notation. You only need to write it once. Everybody see that? Now, what would the range be? Anyone know? The y's. Now, do we have any repeating x's? Do they go to the same y value? So it's not a function. You can't, I always say it like this. Think of the x value as a person. Can a person go to 2 different destinations at the same time? No. Now you're going to see that it's okay when two different x's go to the same y. Two different people can go to the same destination at the same time, but one person can't go to two different destinations at the same time, okay? Now, this is just another way of writing it in the table format. Domain, let me know if I'm going too quickly through this, but it's pretty straightforward. And then we have our range. So this is one of those scenarios. See how 2 and -4 both go to 3? That's okay. Two different people going to the same destination. It's still a function as long as the x's aren't the ones doing it. Okay? Everybody see the difference between those two scenarios?
Yes.
Okay. All right, number 4. Pretty straightforward. And then we have our range. Who thinks it's a function? Good guess, good guess. It's a function. It's definitely a function. Okay. So number 5 is a mapping. Have you seen you've definitely seen these in Algebra 1. Okay. Let's talk about how the mapping works. What are the possible domain values? Good. And what are the outputs?
0, p, 7.
Good. Who thinks this is a function? Take it back.
Same person can't go to
Yes, this is one person trying to go to
2 places.
two places at the same time. We can't do it. It's bad, right? So, I want you to look at something that these two have in common. Look at their domain and range. What do you notice is special about these? My 5, I'm just going to rewrite it because it looks a little weird. Compared to the other ones, what's different about the domain in both these cases? It's smaller than the range. And they're both not functions, right? You see that? Okay, so that's another indicator. If the domain is smaller than the range, that's an indicator that we need to look and make sure that it's, not a function. It's probably not a function.
Can they be bigger than and still be a function?
Can the range be bigger?
Yeah, and still be a function.
Mm-mm. All right. Next one. What's the domain here?
2x, 13, 17.
Good.
2p.
And what is the range? Good. Now, is this one a function?
Yes.
Yes. It's okay for the domain to be bigger. It's just not okay for the range to be bigger. Okay? And it's okay for two different people to go to the same destination. Just one person can't go to two different ones. Does that make sense? You see the difference between that and the one prior. All right? Now we're going to do some graphical ones. So to get the domain with these, you're just taking the x-coordinate of the point. So that's going to be -3. These are both x-coordinate of -3. This has an x-coordinate of 0. This has an x-coordinate of 2. And this has an x-coordinate of 1, 2, 3, 4. So does everybody see where I got those numbers from? Okay. Now we're going to talk about the range. That's their y value, the y-coordinate. The y-coordinate 1, 2, 3, 4, 5, -5. Then we have one at -2, -1, 1 and 4, right? Is it a function? No. And you can also see, does this pass the vertical line test right here? No. So you can tell in a multitude of different ways that it's not a function, right? Everybody in understanding of why that is not a function? Okay. So this one, is this continuous or discrete?
Continuous.
Continuous. We cannot list continuous relations, domain and range, the same way we list the discrete. We can't list it as a set of ordered pairs. Any guess why? Yeah, go ahead.
Yeah, there's no points. There's no.
Well, it's not that there's no point, it's actually the opposite. Yes, go ahead.
It's infinitely.
Very good. There's infinitely many points. That's the word we were looking for. Infinitely many points on this line. Okay? So that's why we can't list them all, because there's infinitely many. We're not here for eternity, listing points, right? So for that reason, we use interval notation. Okay? So how that works is, if we think about domain, we think left to right. What is this function going to do to the left forever?
It's going to be negative.
It's going to go far into the negative values, right? Negative infinity. What's this function doing to the right forever? Positive. So we don't care what direction it's going up, down. We just care left, right for domain. Range is where we care about what it's doing up and down. So if we think about what this function is doing, is it going down forever? Yes. And is it going up forever? And lastly, is it a function? Because it passes the vertical line test. This one is a little bit more nuanced to think about. I'm just going to throw this imaginary dashed line in here just to get you to think about what's happening. Okay? Domain is if it's going to the left, where it's going to the left forever, where it's going to the right. Is this function ever going to go to the left past this dashed line? No. So what's the furthest left that it will ever go? 1, 2, 3, 4. -4, good. And -4 is included, so I use a square bracket. The only time a point is not included and you don't use a square bracket is when they use a straight up open circle or it's infinity. Okay? Otherwise, we include it. And then it's going to go to the right forever, right? So, positive, infinity, always use a curved bracket with that. Now we're going to talk about range. Does it go down forever? And does it go up forever? Is it a function? No, because it doesn't pass the. Look at that, it failed twice. Right there. See that? So, somebody was asking me, well, what if you drew the line over here? It's not a choose your own story, okay? You can't pick a spot just that works. You have to make sure it passes it everywhere, okay? Not just where you pick. Always. Alright. So, sometimes you're going to deal with these bound graphs like a circle. And we're going to determine their domain and range. Alright. So this is bound on the domain between these two values. You see that? What two values are they? -2 and 5. And it's also bound above and below, right? Between -2 and 5. I think it's 5, or is it 4? You're right. 1, 2, yep. Sorry about that. Why did I not use a curved bracket? Good, it's included. That point exists on the on the relation, right? And then, is it a function?
No.
Fortunately not. So 11 and 12 require a little bit of Algebra 1 knowledge. Okay, so I want you to try your best. I'm going to try to give you a little bit of information about these. I'm going to try to get it, to think about it. You to think about it from the beginning. Does anybody know what type of function this is? I kind of gave it away by saying function, but maybe look at the poster under the projector. Quadratic. How do I know it's quadratic? Well, you can tell it's quadratic because of that squared on the x. Okay. Do you all remember what a parabola looks like? A little bit?
Oh, is it that weird smiley face?
Yes, but in this case, it's not a smile. It's a. This one's a frowny face because of that negative. Okay. Now, anybody guess what this +3 tells me?
Y-intercept.
Good. We got a y-intercept at 3. Okay. And then it frowns. And I know it frowns because the a value is negative. Now, I'm not going to expect you to be able to kind of pull this out of your mind right now because you haven't reviewed it in a long time, but I'm just trying to get you to think about things you have learned in the past. So if we think about this picture, I want you to know that every single quadratic function has the same domain. Any guess on what it is? Negative infinity to positive infinity. And that's because as this quadratic goes on, it gets wider and wider, right? And as it gets wider, it's taking on more and more x values, right? Now, the range is not negative infinity to positive infinity because it's bound up and down, right? It's bound up here, so it comes up from the negative direction, and it stops at 3. And if it were flipped the other way around, it would be from 3 to positive infinity, right? Because it'd be going up from there. And if somebody's wondering, well, why do we have to do the negative infinity first? Negative infinity is smaller than 3, right, technically speaking. So it has to come first. We always go number line order. Is it a function? Oh, I meant to say, I said yes in my head, but I was writing no. I don't know why. It's yes. My hand did not want to cooperate. Okay. Any guesses about what type of function this is? Linear with a y-intercept of? And it goes down 1, 2, 3, 4, 5, and then over 1. So it's going to look something like, it's a pretty steep line. Try to get it. It doesn't have to be perfect, it's just a sketch. So it looks something like this. Linear functions have the same domain and range always. It goes up and down forever, and it goes left and right forever. And is it a function? Yes, it is. All right. So I'm going to do attendance. Oh, wait, we got one more thing. I almost forgot. We got two more questions. Take a second if you need, and then we'll do the last two. Okay. Anyone? Any guesses? This is a constant function. Anyone know what it looks like? It's not a vertical line. It's actually a horizontal line. It's at -7. And it takes on every y value that has a y coordinate of -7. Wouldn't that make a straight line? If we think about it, right? Okay. So with that being said, let's think about it logically. What's the domain of this horizontal line? Because it's going to the left and right forever. But the range, however, is it going up and down?
No.
It's staying right at -7. That's the only y value it will ever take, right? If you took any coordinate on that point, would it be anything but -7 for the y?
For the line, why did you put like a squiggly line?
Why did I?
On the range.
Oh, good question. So the reason that I didn't like put a interval is because it only takes on a single value, so I just can put it as like a set. Okay? Good question. Yeah, so if it's a single point, you just put the set notation because we're not trying to talk about a range of values. And then is this a function? Yes, because it passes the... There we go. So you probably have a guess on what the next one is. What do you think? It's a vertical line. So if we think of what happens here, you're going to take that x value of -1, put a point down, and then you just draw a vertical line through it because every single point on that line has a x coordinate of -1. Wouldn't you agree? Okay. So, what do you think the domain of this is? Just -1. And what do you think the range is? Good. Is it a function?
No.
No. Why not?
Because it's vertical line.
Yeah, if I tried drawing a vertical line, it would fail so much, right? It would fail at every point. Okay? Alright, so I'm gonna stop and upload my video.